this course on computational thermodynamics and kinetics of materials. Today we will continue with more hands-on sessions on kinetics. Okay, these are going to be the contents for this class. Hands-on kinetic simulations will be done for a diffusion couple where concentration profile and diffusion path both will be simulated and visualized along with the experimental data. Then we will do non-isothermal transformation. In the previous class we have done isothermal transformation for ferrite growing in austenite. The same exercise we will do in a non-isothermal condition in this class. Then we will see what is parabolic kinetics versus non-parabolic kinetics. Okay. For the diffusion couple, I request you to recall this particular slide that we have seen in one of the previous classes. We have seen that from diffusion couple we can generate input for thermodynamic assessment. I showed this kind of ABC system where we take two end members P and Q, end members of diffusion couple. So the P is here, Q is here after some time, and this T phase, which is shown in the ternary diagram, appears in the middle here, and we can see two phase regions along the interfaces and three phase region at where these three different phases meet. And measuring composition there would be difficult, but that's what gives you the tight triangle information. We have discussed about this in one of the previous classes. And this thing from P to Q, the line that goes here is the diffusion path. We can track diffusion path as well experimentally. Now in this class what we will do is we will find a diffusion couple where after some certain amount of diffusion, this diffusion path we can get and compare it with the experiments. Okay. This is going to be our example. FeCrNi system at 1373 Kelvin and couple of end members. The compositions are given here: ferrite with BCC, chromium 38 mass percent, nickel 0 mass percent. The second end member is austenite, chromium 27 mass percent, nickel 20 mass percent. Okay, two end members are chosen. This end member is almost CrFe alloy because nickel is 0 there, and another end member is a ternary alloy. All three elements are there: 27 chromium, 20 nickel, and the rest is iron. So these two end members will be taken, joined and heat treated at 1373. So the exercise that we are going to do is more like using an example already run and saved in ThermoCalc for the education purpose. We are going to use that. We are going to run that. This is the first sort of that exercise that we are going to do. Let's see how to do that. So after opening ThermoCalc, you can shrink this visualization and expand this project side window. Okay. And click on this example files. Click on these example files here. Okay, so now we are in graphical mode examples for different modules of ThermoCalc, and this diffusion module or DICTRA, this folder will open, and here this FeNiCr moving boundary diffusion couple D05, this example we will run now. Okay, so click on that and open. Okay. Make sure that your project window is wide. So it takes a few seconds. Automatically it populates certain branches in the tree, and it keeps populating multiple stages. And now once it is done, it's stable. So here we can see several things. Okay, they look quite complex now. I'll break it down and explain. In this example, if you see, all these different parts of the tree have different names. The plot renderer is named differently, concentration profile, things like that for our reference basically. But you can see the symbols where plot renderer will have a small graph kind of thing. Based on that, you can recognize what is plot renderer, what is the diffusion calculator stage and all. First, let me remove few points in this which may not be that relevant. So I will remove this position of interface. Okay, and there are multiple times at which the diagrams are drawn. I'll possibly remove one of them so that the diagram is the tree is less clumsier. This 36000 concentration profile. I'll remove, and experimental concentration profile for 36000 seconds, that also I'll remove. Okay, so now this is more or less okay. So I'll explain these things one by one. Now first I'll go to system definer and show you what has happened. Here the two databases that are selected, MFEdemo and FEdemo, this is obvious to you because this FECRNI system, we have these elements in both these databases. So that is selected, that is straightforward. Then in the diffusion simulator, the setup that we do, where we enter data in mass fraction here, mass fraction, and unit is used in meters, and width of the region is given here, that is 0.5, 5 into 10 power minus 4 meter is 0.5 millimeter. Okay, and that is gamma region. Okay, gamma region is here, you can see, that is gamma. Alpha region is here, that is the other phase, which is the chromium iron system, chromium iron end member, that is alpha. So that is here. So alpha is here, you can see alpha's thickness is 9 into e power minus 5. It's quite thinner compared to this. Okay, and the phase in that region is BCC. Okay, so this is known to us. The FECR binary, if you analyze, you will know, or a ternary diagram if you plot, even then you can analyze this. I will also show you the ternary diagram shortly. Okay, so this is one end member which is BCC, the other end member is FCC. So this gamma phase is FCC. The thickness values are coming here by default. I did not give these details in the slides. Basically this is already a built-in example in thermocap, so you can always open and check this. Okay, so this 5 into 10 power minus 4 is the thickness for gamma region. Okay, so this geometric series is used with 1.05, so that in gamma the points are accumulated near this ferrite, near the alpha, and in alpha, if you see, it is the opposite, ratio is 0.8, so that in the right side of alpha near gamma the points are accumulated. Okay, again geometric is the type of points. So this is how points are distributed. Then composition is selected here. Alpha phase composition is given here, where chromium content is 0.38 to 0.38, meaning chromium content is constant throughout, and nickel content is almost 0, that is entered as 1 e power minus 5. This is to assist in the calculation, the software runs better if 0 is entered in this manner. So that is the reason here, convergence would be easier. So this is nickel content, which is 0 almost. So if we pull out this concentration profile, you can see almost 0 nickel here, and this is the chromium content, 0.38, that is the chromium content. So this composition profile for alpha phase. For gamma phase, you can see it here, that is 0.27 to 27, that is chromium content, 28 to 28, that is nickel content. So throughout the entire thickness we have chromium and nickel being constant of this value. So this is the initial concentration profile of two end members. Okay, now in the bottom we can see the time for diffusion. Okay, the temperature is set up here, 1373 Kelvin. So time in seconds is given here, this is 36. Okay, so this is 3600 and 3 more zeros, which is 1000 hours. Okay, so that is how the simulation is set up, right? Okay, so before running, automatically the simulation will not run unless we click perform. Both in plot renderer and the stage of diffusion setup, we will only have the setup and nothing would be displayed now. So you see here concentration profile, nothing is displayed. So we have to run the simulation and see that. Okay. So what I am going to do now is I am going to keep here concentration profile at 3600 seconds, which is after 1 hour. So I am clicking on this box first and then click here perform. Now if I expand this window, you can see this red line, green line, which shows here as, open it, it shows here as W chromium, WFE, W nickel. The blue line, red line and green line, these three different lines you can see. Now what are these symbols here? That is experimental iron content, chromium content and nickel content in weight fraction. That is superimposed here. How do we know this? You can see it here. You see this box we have clicked. I will just drag this box down. See, two arrows are coming and joining this particular stage as predecessors. One is this diffusion 2 regions alpha and gamma, which is the diffusion calculator. Results from that are being displayed here, which are these lines, the red line, green line and all. They are coming from diffusion calculator. Okay, there is another arrow coming here, which is this one, EXP concentration profiles at 3600S. What is this? This is experimental concentration profile data. Okay, you can check how is this experimental data coming here, and it can be integrated to this. Okay, so this is the experimental data superimposed. So what you can sense is there is a very good match between experimental concentration profile and the one that is simulated by the software. Okay, so there is a very good match. Then we can come to this concentration profile here. Okay, 4 zeros, 3 6 5 zeros are there. So we can first click on this 3640, then click perform and see how is the concentration profile and how is the experiment. So you see this, there is again a very good match. Okay, let's go for this even higher time. Okay, so here also you can see a very good match between experiments and simulation. Okay, so these are concentration profiles. So I showed you concentration profile at 3 different temperatures. All 3 come from diffusion simulation that we have done, and the experimental data come from 3 different files. That is this EXP, the files which starts with EXP. Okay, this experimental position of interface also I can remove. Yes, POI we are not tracking. Okay, so the position of interface we are not tracking. So this experimental concentration profile, one file here, second file is here, third file is here. So these 3 files go into these 3 concentration profiles so that we can see them superimposed, right? So after that we have one more diagram to check, that is this diffusion path. Okay, this diffusion path here, there also experimental diffusion path is superimposed. Okay, let us run this and see how is the diffusion path. Essentially we are tracking diffusion path in this composition space, composition of nickel and composition of chromium. Basically we are talking about the ternary diagram, but since we have set up x and y axis without going for a triangular diagram, we will see them in a rectangular diagram like this. You see, so mass fraction of chromium, mass fraction of nickel. If you want you can plot it like a ternary also and check, doesn't matter. So you see here, this is how the diagram looks. Okay, you have a two-phase region here. This is actually a two-phase region. I will superimpose this with the phase diagram and show you shortly. Okay, what we have here is this experimental data showing this two-phase region. Okay, let us bring that phase diagram and connect it here. Go for a ternary calculator. Right click here, right click on system definer, create new successor, equilibrium calculator. Okay, so this equilibrium calculator, let us bring it here. Here what we want is a phase diagram. Want a phase diagram. We'll keep nickel content in the x-axis just like this, mass fraction of nickel. Okay, let's change the unit to mass fraction. Mass fraction of nickel in x-axis and mass fraction of chromium in y-axis. Okay, 0 to 1. And let's keep the temperature here 1373 and run it. Perform. Okay, so calculation is over. Then we'll go to this diffusion path, right click and add the predecessor equilibrium calculator so that the calculation results can come here. Okay, now it has come here. In this diffusion paths plot renderer, you can see equilibrium calculator and the diffusion calculator, both are connected here. Okay, so the equilibrium calculator, if I click that, then I can do this change here, mass fraction, whatever is displayed in this diffusion calculator, I want same thing there. 0 to 0.4 of nickel with 0.1 stepping, 0.2 to 0.45 for chromium with 0.1 stepping. I'll do the exact same thing here. 0 to 0.4 for nickel, and here 0.2 to 0.45 for chromium. Okay, so let me perform now. Okay, yeah, now you can see the diagram with the tie lines. Okay, let me remove tie lines for the clarity, and also stable phases, I'll switch them off, then perform. Okay, now you can see this region is this two-phase region BCC plus FCC, and this region is single phase BCC, and this region is FCC single phase. Okay, you can see this is our initial end member, one end member, this is the other end member. So these two end member compositions, when they are joined, this is the diffusion path. Okay, that you can track. So beautifully the experimental data is reproduced in the simulation. Okay, this experimental file has some particular formatting. If we remove that, then we can visualize this in the ternary diagram, triangular type. Let's do that. So remove predecessor experimental diffusion paths, and then go to select this triangular type and run. Okay, so now if I open it, you can see the diffusion path nicely following the tie line. Okay, this is the initial end member, the first end member and second end member. Now nicely this diffusion couple traces this diffusion path in the phase diagram. You can see that. Okay, right. So let's see the next example. So this is going to be again the moving phase boundary problem, the one that we have seen in the last class, where at 800 we have simulated the growth of ferrite inside the austenite. We brought down the austenite from high temperature to here, and the ferrite grew inside, and this was done at isothermal exposure at 800, right? So in this class what we will do is we are going to do that in a non-isothermal fashion, cooling from 1173 to 1050 Kelvin over 1000 seconds, but in a non-isothermal manner. I will show the profile shortly. And this is an example, inbuilt example in thermocalc. This example number is D04. Let me run it and show you why is it non-isothermal and how the end result looks compared to this one. Okay, I'm going to open this example files. Diffusion module and DICTRA examples. D04 diffusion FEC moving boundary austenite to ferrite. This example I'm going to click and open, and it takes few seconds for it to populate different parts of the tree. Now it's done. I'll show you in the diffusion calculator stage what is the difference compared to the previous class exercise. So everything else most of the things remain the same compared to the last class exercise. This thermal profile is different. It is chosen as non-isothermal, and in Kelvin simulation time 1000 seconds. But if you see the profile is given here, time 0 second, 773 second and 1000 second, and for those particular times we have this temperature going from 1173 to 1050, then staying at 1050 for some time. So 773 seconds to 1000 seconds it is constant, but between 0 and 773 it decreases from 1173 to 1050, and this is the thermal profile here. Okay, so it decreases from this temperature to this temperature in this linear fashion and then remains constant. So, okay, so this is non-isothermal in nature. Let's see how the results look in this case. Okay, so I'm going to click perform tree, let the calculation run. Our calculation is over. I will click on this carbon composition profile. These profiles are drawn at different times. Okay, 400, 600, 800, 1000, different seconds. You know, between 773 to 1000, it was at isothermal condition. Since 800 second and 1000 second are exposed at 1050 degrees Celsius, the Thailand information that we see, the phase diagram, according to that, two compositions are seen. This is the composition of austenite, this is the composition of ferrite. Okay, so mass percentage of carbon you can directly read here. Because it is, these two are from same temperature, you can see the concentration of carbon is same. Only thing, it is shifted due to growth of ferrite. But look at the red one and the blue one. These are for higher temperatures, different temperatures. Okay, so 400 and 600. This is 600, where the temperature should be slightly lower. Therefore, you can see the Thailand information is different. Therefore, the equilibrium composition of the two phases are different. Okay, at 400, it is even more different. Okay, this is how the composition profile evolves as the time progresses for a continuous cooling, okay, non-isothermal profile. Now what I am going to plot is one more plot renderer here, create new successor plot renderer. I will show you position of interface. That's what we tracked in the last class, right? So let's check that one. Time against position of interface. Okay. BCCA2 or BCCA2 or austenite. This is the interface. Click perform and see how does it look. You can see this is in this shape. Okay, this is definitely different compared to what we have seen in the isothermal. In isothermal it was a smooth parabolic curve. Here it is not so. Okay, let's compare them and understand what is parabolic kinetics and non-parabolic kinetics. Okay, in parabolic kinetics we see that in this kind of processes, the processes are diffusion controlled. We'll contrast this with the interface controlled in a couple of slides. Wait for that. So isothermal processes where only diffusion takes place, for example carburization, or isothermal process where transformation with single interface movement happens, for example ferrite growing inside the austenite in steels, the exercise we have done in the previous class. Okay, these were parabolic in nature, like this. Okay, this was the curve that we got in the last class. Position of interface was in this shape. This is a parabolic growth. Okay, that is ferrite austenite interface movement in steels for isothermal conditions. Okay, so kinetics of the process there, it was obtained by solution to Fick's second law at isothermal conditions. Okay, the position of interface x is proportional to root of time, or the position squared is equal to k multiplied by t. So this is equation of a parabola, if you see. Okay, so this is parabolic nature, and this k is called parabolic rate constant. This most of the simple diffusion controlled processes, isothermal conditions have this kind of nature. Okay, so in this class what we have seen is this kind of curve. Okay, this is definitely not parabola. Okay, so diffusion controlled processes in non-isothermal conditions, where even if it is single interface movement like this ferrite growing inside the austenite, it need not have parabolic growth, because these non-isothermal conditions make this rate constant, which is dependent on temperature, quite complex. So the kinetics of process here need not be parabolic. And to understand this better, let's understand what is diffusion controlled against interface controlled. Movement of interface is fast in diffusion controlled. It is assumed to be infinite. So interface is not at all causing any problem. Only jumping of atoms, the diffusion is difficult. Okay, so diffusion is slow, and hence it controls the rate of the whole process. Okay, whereas in interface are mixed control. Mixed means interface and diffusion control. In these processes what happens is movement of interface is finite, it is not infinite. It is slower, significantly slower maybe compared to diffusion, or comparable to diffusion. Okay, so if it is significantly slower, we can say it is definitely interface controlled. If it is comparable, we say it is mixed control. So kinetics of the process in these cases will not be parabolic. Okay, the nature of interface or mixed control processes are handled in the overall transformation kinetics. We will see that in next couple of classes. This overall transformation kinetics is important because this is going to cover most of the transformations, because transformations involve something called nucleation growth where interface matters a lot. That will be difficult compared to mere diffusion. Okay, we'll dedicate a class for the fundamentals of it and then move forward. We'll see that after the next class. Thank you. I hope the lecture is useful. See you in the next class.